Welcome to this video on Karnaugh Maps in many variables. We will cover how to apply the Karnaugh Maps theory from last video so that we can use it for 4, 5, and 6 variables, but the rules can be extended to more variables. This video highlights how Karnaugh Maps are an irreplaceable tool in more complex system design. We start by looking at a 4-variable Karnaugh map example. You can see the truth table, which represents all possible combinations of zeros and ones. That represents the numbers 0 to 15. The outputs have been chosen so they are true when a multiple of 2 is detected, as we want to design a multiple of 2 detector. We can transfer the contents of the truth table to a Karnaugh map as follows by the color coding. You can see that the Karnaugh map sides have been labeled with A, B, C, and D, as well as the combinations 0, 0, 0, 1, 1, 1, 1, 0. The order of this has been done so that as we move to adjacent cells, only one bit is changing at a time. This is called gray code. Now, just as we did in the 2-variable Karnaugh map in the last video, we can loop ones until all of the true outputs have been included at least once. We can see that where C has no effect, we get A, B naught, D naught. Where D has no effect on the output, we get A, B, C naught. Where A has no effect, we get B, C naught, D naught. And where B has no effect, we get A naught, C, D naught. Note that when the variables are written next to each other, in Boolean equations, this means an AND gate. In order to find the Boolean expression for the multiple of 2 detector, we combine all of the expressions together using an OR gate into one large expression that covers all eventualities of true states in the output. This is done in the most simplified way. This circuit shows the final design, which can be implemented using standard gates to achieve the desired functionality. Although this looks complex, if you try each input combination, you should get the same truth table as before. This highlights why it was important for computer hardware to be able to be implemented on smaller chips to allow for the computers and phones we have today to be possible. Moving on to 5 and 6 variable Karnaugh maps. We can see that this is representative of the rules that would be needed for 7, 8, and more variable maps. We can see that we need multiple layers, but as we can only have 4 variables on a map at a time, a layer needs to correspond to a certain variable not changing, such as A and A naught in the 5-variable case. The same rules of Karnaugh maps applies, but we can loop between layers as well. We conclude with some final remarks. Karnaugh maps in many variables has been explained in this video, with an example of a 4-variable Karnaugh map. You should now be able to see how Karnaugh maps help you to make sense of increasingly higher complexity. Like and subscribe for more.